Yeah.
Yeah. Okay. Cool. Thank you. So sorry about that, folks. I will have to take a look at the technology later. I feel so bad because yesterday's lecture didn't end up recording, and then now we're having some difficulties today. But okay, so let's jump back into our lesson from yesterday. All right, can you folks see the screen?
Yeah.
Yeah, okay, you can see the notes from yesterday? Okay, so here we go. Again, my chat window is not super visible to me, so I'm gonna, if I don't see a question in the chat, my apologies. I'm not ignoring you. Okay.
I have a quick question.
Is it about the technology?
No.
Okay.
It's about the polar coordinates.
Okay, I'm gonna ask you to maybe save that for a little bit later, okay?
Okay.
Okay. Can you guys hear me, and is there any sort of feedback right now? Like
Yes.
negative feedback?
No feedback, I can hear you.
Okay, all right. So the reason why I'm asking is because I actually pulled it up on my computer as well, so I can see the chat window now if you want to enter things in the chat window. But if there becomes some sort of feedback, then I'll log myself out of the other device. All right, so let's do a quick summary of yesterday, and then Mariah will take your question, and then we'll move on. So 13.3, we talked about yesterday, is really an introduction or a review of an alternate coordinate system, right? So we know about rectangular, and then hopefully we learned about polar coordinates in pre-calculus. And the reason why it's coming back up now is because in your next course, when you all are so very grown up and taking Calc 3, it's important to have the foundation for polar, because you're going to take all of these polar shapes that we're talking about and actually think about what happens when we revolve them or rotate them and end up with a three-dimensional situation, okay? And as you can imagine, given our sort of world today, three-dimension is often much more useful than two-dimension. All right, so we talked a little bit about graphing polar coordinates. We talked about that first number being the R, how many circles you count out, and the second number being the angle, or theta, and that's the one you actually go to first. So you find a specific angle, and then you count out a certain number of circles in a given direction. So if that first number is positive, you go in the direction of the angle, but if that first number is negative, you go in the opposite direction of the angle. All right, so then we also said, and this is probably one of the most important takeaways, there can be more than one name for any given point in polar. So it's not like the rectangular where you have an X and you have a Y and that's the only name you can call it. There are multiple ways to label a point in polar. So then after that, we took a look at converting between rectangular coordinates and polar coordinates. We kind of did this using what we know about right triangles. And then at the end, we summarized it with these formulas here, okay? So we could kind of see if we need formulas to convert, why we have them the way we have them and where they came from, right? So we talked about that tangent being the typical way that it's presented in like a textbook or a video, but that you could, once you find the hypotenuse, we could use arc cosine or arc sine if that happens to be easier for us to think about in terms of finding angles on your unit circle, okay? I think that part was pretty straightforward. I think what really started to get a little uncomfortable for some of us is this idea of not just converting a coordinate, but an equation. And that when we were converting the equations, we had all these formulas, but we kind of needed to think about what substitutions made the most sense. And so in examples 5 and 6, it was a little bit more straightforward because we had the x squared plus y squared. And so we could replace that with r squared right away. And similarly, in example 6, we had this y, and we were able to replace that with the r sine theta because that was simply one of the equations that were given. But then I think where things started to get a little bit messier, or not messier, but took a little bit more intuition, is in example 7 and 8, where we had to go back and think about, what is the best way to do a conversion, and remembering that at the end of the day, we might have different methods of approaching this. Some people might like to get rid of fractions. Some people like to make the substitutions right off the bat. But at the end of the day, through some trial and error, we were able to get to 2 different forms of the same answer, okay? And thinking about if we wanted to just find the equation, that there is nothing wrong with this version. We didn't even have to solve for y. But if we were thinking ahead that maybe we would use it for derivatives or integrals, that's where this second form, getting rid of that square root, might make our computational lives a little bit easier. Okay, so it's sort of like pros and cons to the different forms. And then with number 8, that was a throwback to one of the more common trig identities, that sine double angle formula. And then once we had that, being able to manipulate our equations that were given so that we can make our substitutions and achieve that goal of, if we want rectangular, we should only have x and y. And if we want polar, we should only have r and theta. Okay. So let me pause here for a moment. Are there any questions about sort of this first chunk?
I just had the quick question about the polar chords.
Okay.
Are they considered quadrantals, or is there another name for them?
Are they what?
Are like the poles considered quadrantals, or is there another word for them?
You don't necessarily have quadrants in the polar because it's just the pole and then rotating around that. But if you layer it with the rectangular one, then certainly you can talk about quadrants in that sense.
Because with the pattern with the even or odd functions, you saw whether they were intersecting. What we saw originally back years ago was quadrantals, but I didn't know if that was what they were named now or not.
I don't actually know if there's a name for them, but I'm going to guess that it's not quadrantal because we don't have quadrants in polar coordinates.
Okay, so they either cross a pole or they don't.
Right.
Thank you.
Okay. All right. So then at the end of class, we were sort of running through a few different types of graphs. And I don't mean to say, hey, play around with Desmos in a dismissive way, okay? I don't say that to be like, oh gosh, if you don't know this, just go learn it on your own. I genuinely think that Desmos is a pretty cool, free, 100% free tool where you can use to help you visualize and see these patterns, okay? So if you do not already have Desmos on your phone or on a tablet, or you can just access the website. You don't need a phone, a smartphone, or a tablet in order to access this. As long as you have the internet, you can access Desmos. And there's a setting for polar, so you can play around with the equations that we have here, okay? I've included a few examples just so we can kind of get the idea. I know that it's not anywhere enough time for you to really get all of these patterns memorized, but I do want to just kind of get you started so that when you do play around with Desmos a little bit, start to change some numbers, see if you can understand like what the different numbers represent in the polar equations, okay? Because just like we have like y equals mx plus b, and we know that the slope is always m and that our y-intercept is always b, these numbers do specific things for the different graphs, okay? So we talked very briefly about lines. It's not a super common shape for a polar. We tend to look at more like wavy looking things or round looking things, okay? So the line is not necessarily a super special polar one, but I did want us to understand we still can create a line in the realm of polar, okay? And then we talked a little bit about Archimedes' spiral, so that we have these spirals that go in different directions, or they go in the same direction, but they start at different places, okay, starting at a different angle. And that's only because you have a positive versus a negative theta, okay? And again, that's something that if you play around on Desmos, you could kind of see what happens if you put like a number in front of theta, or what happens if you make it negative and you put a really big number or a really small number. Okay, and so those are all things that you can sort of play around with on your own time. But I did want to highlight that like this is a common kind of polar shape, okay? Then we started to talk about circles, all right? So we know that from some of our equations earlier that we could find a circle centered at the origin, and that polar equation was actually very straightforward. R equals whatever we have for the radius, okay? But what was significant is that when we looked at circles that were sort of up and down or right and left from the origin, that the up and down ones had a sign in the equation, like a sine theta, and the right and left ones had a cosine theta in them. And that number in the front no longer represented the radius, but it actually represented the diameter, okay? So this number is actually the diameter of the circle. And then similarly, this number, that 4 in front of the cosine, is the diameter of that circle. Okay, so that's why we had a radius of 2. And then we talked a little bit about symmetry, and then I was like, here's a list of things that you should just know about symmetry. And so I actually want to go back and kind of do that a little bit more today. And then we'll kind of review the rest of what we talked about, okay? So specifically, I want to take a look at this case right here, the one with the sine. And I said that the theta equals pi over 2 is the line of symmetry, or whatever we consider the y-axis in a rectangular coordinate, okay? But I want to show us algebraically sort of why that's going to be true, because you can use this idea of symmetry to help you, again, when you're finding area, to say, okay, here's the line of symmetry. I'm just going to go from the line of symmetry to one end, and then I can double my answer at the end, okay? So this equation was r equals 4 sine theta. And if I wanted to think about things being symmetrical about that line, theta over 2, then what we can do is we can substitute pi minus theta for theta, okay? So if there is that symmetry, we should be able to substitute that. So let's see what happens. If we substitute, we keep the 4, but instead of sine theta, we put sine of pi minus theta, okay? So that's that rule of symmetry, the substitution we can use. So let's see if we expand this algebraically, can we match these two equations? Because if we can, then we know that symmetry is true, okay? And so the trick that we use to expand this sine of pi minus theta, there's 2 different ways, but I think one of the more common ways is that we think about the sine, sum, or difference rule, okay? And that rule, or that identity, is sine of the first angle cosine of the second angle minus cosine of the first angle sine of the second angle, okay? And then we can substitute any values that we know. So for example, I know that sine of pi is 0, okay? And I know that cosine of pi is -1. And so when I make those substitutions, I end up with 4 times 0, because 0 times cosine theta will be 0. And then I have minus a negative sine theta. And when we combine those signs in between, 0 minus a negative sine theta, I end up with r equals 4 sine theta, okay? So because this is equivalent to this, that is confirmation that my shape has symmetry along theta equals pi over 2, right? And we can see that from the picture, that the right half and the left half are the same. So we can do the same thing for the cosine one, but it has a different line of symmetry. This one has symmetry of theta equals 0. So let's go back to that little chart and see what substitutions we can make here. So if it is symmetric about the line theta equals 0, then the substitution I can make is everywhere I see a theta, I can put in a negative theta, okay? All right, so let's make that substitution. We had originally r equals -4 cosine theta. And if that symmetry is true, when we say r equals -4 cosine of negative theta, we should be able to simplify it to get to the same thing that we started with. And so when I think about the cosine function, okay, the cosine function is even. That means that cosine of negative theta is the same as cosine theta. And so I end up with -4 cosine theta, and this are equivalent. So that confirms what I saw in the picture, that there is a line of symmetry at theta equals 0, okay?
Can I ask a quick question?
For sure.
I can't seem to remember. How do we know if it's even on this? I'm sorry. The
So
cosine.
cosine and sine, those are good ones to know. So cosine looks like this.
Oh, through that. Okay. All right.
And then sine looks like, well, sine looks like this. Right,
Okay,
so
perfect.
one is even and this is odd.
I appreciate it. Thank you.
Of course, of course. All right. So you might be like, why is the even odd thing important, or those lines of symmetry, right, if we have a picture? And part of this is you might not always have a graphing tool available or whatnot. You might need to just sketch a quick picture, and it's just kind of nice to know what's even and what's odd, or where the lines of symmetry are, so you can get to those diagrams faster, so that like all the stuff we're going to learn today, like finding derivatives, finding integrals, all of that stuff is really where we can focus our brain power rather than coming up with the graph, okay? All right. So then after the circles, we took a look at the rose curves. And this is the last thing that we covered at the end of class yesterday, okay? And so when we looked at the rose curves, we looked at 2 different cases, like what happens when it's even versus odd. And remember, for even ones, the number that is in front of the theta tells you only half of the number of petals, right? So in those first 2 examples we saw, if I have a 2 theta, that means I have 4 petals. What happens if I have like a 8 theta? How many petals do I have?
16.
Yeah, if I have 8 as my n value, I'm gonna have 16 petals. Now that means that I go all the way around this unit circle, like from 0 to 2 pi, okay? If I only go from 0 to pi, I will only see half of the number of petals. So in general, with the even ones, we're gonna integrate from 0 to 2 pi if we need to find all of the petals, okay? But then at the end of class, we talked about this, which is definitely important, where if we integrate from 0 to 2 pi for odd numbers, we'll actually get twice as many petals, but they're on top of each other. So then the picture might not look different, but we end up with a number that's twice as big as our friends who might be only integrating from 0 to pi, because we're double counting the layered petals, okay? And so for odd values of n, we want to only integrate from 0 to pi, or we only want to go halfway around the unit circle so that we only get the number of petals and we don't double count, okay? All right, so before we move on, are there any other questions that are coming up for folks?
I have one.
Yes, what's up?
So for when you're integrating, it doesn't matter whether or not it is even or odd. If you integrate from 0 to pi, it will give you n number of petals.
Yeah, yep.
Okay.
Yep. That's a great way of saying that. Okay. All right, so we've got a few other shapes to cover today, all right? And then we're gonna take a look at some of the more fun stuff like finding slopes at these different points on a polar curve, finding area of petals or arc length of certain regions, all right? So every year when I teach the Limas Chart, I feel like I come up with a different graphic organizer for it. So if you had me for pre-calc, this looks a little bit different, hopefully different in a better way because I didn't really like it the first time. But so the Limas Chart is a special equation where you have something of the form r equals a plus or minus b cosine theta. Now we're looking at the ones that have cosine, but in just a moment we'll learn we can also have a sine theta instead. All right. Similar to what we've seen before, cosine theta is going to have symmetry around theta equals 0, but sine theta ones will have symmetry around theta equals pi over 2. So similar shapes, but different axes of symmetry. So the Limas Chart has two numbers here that are important for us to look at, okay? So it has an a value, all right? So that's the number that is not directly next to the sine or the cosine. And then there is this b value, okay? So the b value is the coefficient for the trait. And so if we take a look at some of these shapes that we have here, okay, what's really important in defining these shapes is the ratio of B to A, okay? So if I take a look at this first one, my A value is 2. What's my B value?
1.
1. Okay, so I'm going to put the 1 in there just so I know. All right, so I've got a B of 1, and I've got an A of 2. I think I typed the letters backwards. So sorry. Let's just change this. Okay, So let's take a look at the A value. The A value here is 2, okay? And the B value is 1. And 2 divided by 1 is 2. So in the case where A over B is 2 or bigger, you're going to end up with a shape that looks like this, and it's called a convex limmason, okay? So we've got, this happens when A over B is greater than or equal to 2. The convex part is not that it does kind of bulge out, but more than bulging out, it just doesn't have an indent or a divot, okay? So like this part right here is the part that makes it convex. You know, I chose the horizontal ones because I thought they looked less like butts, but they still look a lot like butts. So sorry about that. All right, so let's move on. Let's take a look at some more of these A and B values, okay? So the A value in this second one is 1.3. And the B value, like the first one, is 1. Okay. And so if we take a look at A divided by B, we'll get 1.3 divided by 1, which is 1.3. Okay. Now, when the ratio of A to B is between, it's less than 2, but it's greater than 1, then what you end up with is what we call a dimpled limmason, okay? So it's like a very slight indent right here, right? That's the part that makes it dimpled. And then again, this happens anytime you create some numbers where that ratio is between 1 and 2. All right, I also realized I spelled cardioid wrong in everything. It should have an I at the end, ID, okay? So you get a cardioid when your B value, in this case 1, and your A value, which is also 1, when they happen to be the same number, okay? So our A value is 1, our B value is 1, and we get a ratio of 1. So anytime A over B equals 1, we're going to end up with a cardioid, okay? They call it a cardioid because it's supposed to look like a heart, right? So if you turn your head sideways, it kind of looks like a heart. But again, this part right here, see, it's a little bit of a larger indent than the dimpled limmason. That larger indent is the reason why we call it a cardioid, okay? All right, so what happens if our ratio is between 0 and 1, okay? So our A value is 0.5, our B value is 1. So we have 0.5 divided by 1, which is 1/2. Okay. And so when we have an A over B that is between 0 and 1, what's going to happen is we're going to get a little inner loop, okay? So the inner loop is this part right here, okay? So when that ratio gets between 0 and 1, we're going to end up with an inner loop. And so those will be some of the questions we take a look at later on, where we're like, okay, I don't want to find the area inside the whole shape. I only want to find the area inside the inner loop. And so that's where it becomes really useful to know the bounds of how we get that inner loop, okay? And then our last case is when A is 0 and B is 1. And it doesn't really matter what B is, but if A is 0, anytime A over B equals 0, we degenerate back into a circle, okay? So the circle that we saw earlier is actually a very special case of the Limas song. All right, so here's a little chart just to help you kind of remember what those different shapes are, all right? But again, each one of these, we can find the area inside, we can find the area in part of it, we can find the area between two of them if we layer them on top of each other on the same graph. We could also find out the slope at different points, and that's sort of where we're going, okay? All right, so let's move on to the different cases of symmetry. Okay, so we saw a lot of cases of symmetry with the cosine, like that whole last table was only the cosine one, but I want to show us like what's different about the sine ones, okay? So we're going to use a little table to help us plot a few points, all right? So for r equals 2 plus 2 sine theta, all right? I noticed that the multiple or the coefficient of theta is 1. So I'm just gonna do nice unit circle values, meaning I'm gonna choose 0, I'm gonna choose pi over 2, and I'm gonna choose pi, because those are values where sine is either 0 or 1 or negative 1. And so it'll make the mental math easier, right? When we have a table, the goal of the table is to make it easier for ourselves. The goal is not to create like a situation where you have these crazy decimals. So I saw a few people who were graphing some of the parametric stuff, and you had these tables that were giving you not nice numbers. But remember, we're trying to create a table to make our lives easier. So we really want to be clever about how we pick the input values so that the output values are easier for us to compute. So what do we get? When we plug in 0, we're going to get an R value of 2. When we plug in pi over 2, we're going to get an R value of 4. And when we plug in a theta value of pi, we will get 2. Okay? So let's plot those points and see what we get. So at an angle of 0, I'm going to go out 2 circles. At pi over 4, I'm going to go, or pi over 2 rather, I'm going to go up 4 circles. And at pi, I'm going to go back out 2 circles. Okay. So if we wanted to think about the shape, all right, we end up with this part is sort of like the part of every limaçon that's the same, like that rounded edge, okay? Now, in this case, which one of those situations from the previous page are we going to have? Are we going to have a convex limaçon, a dimpled limaçon, a cardioid, an inner loop, or a circle?
Convex.
Cardioid?
Yeah, we're going to get a cardioid. How did you know that?
Your A over B is equal to 1.
Yeah, we got an A value of 2, a B value of 2, 2 divided by 2, whoops, gives you 1, which means you have a cardioid. Okay. So you can sketch the rest of the shape just by knowing if it's a cardioid, you shouldn't have any inner loops. It's not going to be a circle, so you just go ahead and do something kind of like this. So it's like a heart, but facing down, okay? Any questions about how we generated this shape?
How do we know that the heart point is at the origin?
Because all of these are centered at origin.
Okay, are we going to deal with cases where they don't?
No. You might in the future, but we won't right now. Okay. So if we take a look at the cosine one, all right, we know that if we have a plus b cosine theta, it's going to be one that is symmetric along theta equals 0, all right? And so in this case, let's do a little bit of pre-thinking. I've got an a value of 2. I've got a b value of 4. So 2 divided by 4 gives me 1/2. So what shape are we going to have for this second example?
Good luck.
Yeah. We're going to end up with an inner loop, okay? Now, if you're not confident, like 3 points is not enough for you, plug in more points, right? You can plug in as many points as you want to help you feel confident that you have the shape that is appropriate. But knowing that we're layering this on with calculus, again, I'm trying to get us to feel more confident on this so that the calculus work is really where we're focusing, okay? So for our cosine one, let's pick the same theta values, 0, pi over 2, and pi, all right? And so when I plug in 0 into this equation, I'm going to get, let's see, 0 plus, 2 plus 4 is going to give me 6, okay? If I plug in pi over 2, I'm going to get 2. If I plug in pi, what value am I going to get for r?
6.
No.
Oh yeah,
Negative 2. Yeah, right? Because cosine of pi is -1. All right, so this gives us, thank you, Kevin, I saw that. So this gives us a few points to at least plot and kind of get started. So at 0, I'm going to go out to 6, which is right here. Pi over 2, I'm going to go over up 2 circles. And at pi, I'm going to be at -2. So where is that point? Where is that point -2 comma pi?
Still along the x-axis, but moving towards 0.
Yeah, it's actually, so pi would be here, but I need to go -2, which means I'm going in the opposite direction. And so that would get me right here as the third point, okay? And so when we connect these, and again, you can use as many theta values as you want. I'm just giving you an example of how you can find these. You would know that you have sort of this part of that limaçon. And because of symmetry, I can even sketch in the bottom part because I know it's symmetric around theta equals 0. And so now I just need to create that inner loop. And that's what that third point gets me, is I'm going to come through here and I'm actually going to create that inner loop. Not like that. Stop correcting that. So like here. And then I'll come back through the origin. And so I've got my limaçon with an inner loop. It's got symmetry along theta equals 0 because it is a cosine one, okay? All right, any questions about the limaçon?
Well, when you're plotting the pi and the -2, you just go 180, and then you go to the right again, 2 units?
Yes.
Okay.
So if it were a +2, you would go to pi, and then you would go to the left 2, right? You go in the direction of the angle. But because it's a negative, you go in the opposite direction of that angle.
All right.
Okay. All right. So let's do one last shape, okay? So there's one last shape called the Lemnos Gap. This one is pretty easy to recognize because it's the only equation that has an r squared and not an r, okay? Now, what that means, if you are gonna take some time and play around on Desmos, I'm not sure if they allow you to put in r squared. Sometimes you have to type it in as r equals the square root of the other side. Okay, so if you're gonna use Desmos, I would try doing that. All right, so very similar to all the other stuff we've seen. If we have theta equals, if we have a cosine one, then it's going to be symmetric about theta equals 0, okay? But one thing that is a little bit different in this case, and this comes from the square part, is that the sine of 2 theta is actually symmetric about the pole, and that's sort of what you can think about like the origin, okay? So when we draw one petal, this one actually has petals as well, when we draw one petal, we're not just going to reflect it over the theta equals pi over 2, we're actually going to reflect it about the origin, so more of like an odd looking function, okay? All right, so given this equation, r squared equals 9 sine of 2 theta, what might be some good angles to pick for my theta if I want to make a table?
Pi over 4.
Okay, so I'm going to start with 0, right? Because I always want to start with 0, but I agree that maybe we could count by pi over 4. So pi over 4 and then pi over 2. Okay, and we could, if I sort of peek ahead to the other side with the cosine of 2 theta, I probably want to use the same input values. Okay, so let's find our r's. So if I plug in 0, I'm going to get 9 times 0, which is 0, and so the square root of 0 will give me 0. If I plug in pi over 4, that's going to give me 9, and so r squared equals 9. What is the value of that, of r?
Plus or minus 3.
Okay. And if we get back to pi over 2, we're going to get another 0. Okay. So if we start to plot these points, we've got our point at the origin, 0, 0. And then at pi over 4, we're going to go out 3 circles. Okay. And at pi over 2, we're going to be back at 0. And so this gives us our first petal. It actually also gives us that second petal because we have the -3, right? But you can also say, I know this is odd or it's symmetric about the origin. So this petal, when I reflect it across the origin, will be in the bottom left part. And I'll get one like this. It's kind of like a bow tie, okay? Now the length of each petal is the square root of this number, right? So if it's 9, the petals are not going to be 9 units long, they're going to be 3 units long. That number were 16, the petals would be 4 units long. What if that number is 5? How long is each petal?
Root 5?
Square root of 5, right? So I think sometimes we get so uncomfortable with that square root, we're like, 5, but we still have to take the square root of that number, okay? All right, so if we do the same thing for our r squared equals 9 cosine 2 theta, we fill in our table, we're gonna get a plus or minus 3 here, we're gonna get a 0, and we're gonna get, what are we gonna get over here when we plug in pi over 2?
You're going to get plus or minus 3i.
Okay, so that's something to kind of think about, like what values can you plug in, what values can you not plug in? But if we plot these points at 0, we have our 1, 2, 3, and our 1, 2, 3. And at pi over 4, it's going to be at 0. And so we have like the ends of our bow tie and the center of our bow tie. And so we can go this. Okay. And again, the petal length is going to be the square root of a squared, whatever that is. Okay. If you did not have a great experience in pre-calc, or it's just been a really long time since you've seen Polar, I would really encourage you to play around with Desmos. I do think it's one of the best tools out there to kind of help you visualize things. There are also a bunch of videos out there on the internet if you're like, this wasn't really sticking for me, I really want to go back and like hear it again from someone else. That's totally fine. But again, I would encourage you to really know, like, if I see this equation, this is the shape that it's going to be. If I see this equation, this is the shape it's going to be. And being comfortable either like memorizing what shape and what orientation, or being able to quickly, and that's sort of the key word here, quickly create a table. Okay? Because again, if you are going to Calc 3, the expectation is you just know what these look like. So if you're not there yet and you want to be in Calc 3 in the fall, I would use this as an opportunity to make sure you know what these shapes look like. Okay? So we are going to stop here. Okay? So I'm going to stop the recording. And Lindsay, if you don't mind stopping the video.
Okay, did you want me to pause it or stop it?
Stop it. That way we can start a new one, or maybe I'll try and see